Okay, let's continue where we left off. First, I want to recall the later result from the previous lecture. So we proved the Lagrange Theorem. What was that? That was a claim, the Lagrange Theorem. Let's say, let's not write the surname here. So if we have a finite group, and inside that finite group we have a subgroup, which is necessarily finite. Then the size of the group, the order of the group, is equal to the amount of cosets. It doesn't matter left cosets or right cosets with respect to the group H times the size of the subgroup. That was the Lagrange theorem. Now I want to formulate several corollaries from this theorem. So the immediate corollary number one. So, oops. Let's say corollaries. Corollary number one, well, says simply that if you have a subgroup inside a finite group, then its order divides the order of the group. Well, this is an immediate corollary from this statement. The next claim is a bit more interesting. If we have an element of a finite group, then its order divides the order of the group. For example, if you have a group of order like 18, well, you may not find an element of order 5 inside because 5 doesn't divide 18. So this is a restriction for an order of an element. So why this is true? Well, because the order of an element is equal to the order of the cyclic subgroup generated by the element. And this thing, because of the previous item, divides the order of the group. So this is the corollary number two. And the corollary number three says that if you take an arbitrary element from the group G and raise it to the power of the order of G, you will get the identity element. Well, why? Well, this is because of the previous corollary. We have the order of the group to be equal to the order of the element G times some integer k, because order of the element divides the order of the group. But then G to the order of the group is equal to G to the order of G to the power of k, and this thing must be the identity element just by the definition. So you have this, and then we will get that. So again, this is just a simple corollary. Now, the corollary number four says if you have a finite group of prime order, then P is prime, then G is cyclic. But we can formulate this more precisely. For every element of G which is not equal to the identity element, G is generated by the G small. So every non-identity element of the group G is a generator of G capital, and hence G capital is a cyclic group. Okay, so let's see why. So this is only if the order of the group is prime. So let's see why this is true. Well, let's take an arbitrary element of G, which is not identity. Then consider its cyclic subgroup. First of all, this is a subgroup inside G. So because of the Lagrange theorem or any other previous item, here we know that the order of this cyclic subgroup must divide the order of G, which is prime. So we have actually only two options. The option number 1 is the order of this subgroup is 1. The option number 2 is the order of the subgroup is P. But now, since the element G is not equal to the identity element, this option cannot hold. This is impossible. Why? Because this subgroup contains element 1, and it also contains the element G, and they are different elements. So the order of the cyclic subgroup is at least 2. So it cannot be 1. So that's why the second option holds. But in the second case, this simply means that the cyclic subgroup of G small coincides with the whole group G. And this is exactly what we wanted to prove. So this was the corollary number 4. And the later corollary is the Little Fermat theorem. Corollary number 5. Well, suppose P is a prime number. A is an integer such that P doesn't divide A. Then P divides A to the P minus 1 minus 1. Or you may reformulate this as A to the P minus 1 is equal to 1 modular P. So this is the Little Fermat theorem. So now how to prove this? Using the Lagrange theorem, we need to consider the group ZP star with multiplication, which is the set of all remainders modular P that are co-prime with P. So we exclude the 0 elements, so these are non-zero remainders modular P, and the operation is multiplication. So this is a group. And the order of this group is equal P minus 1. Why? Well, because the order of ZP is P, and we excluded just one element. So this is the order of our group. And because of the corollary 3, we know that if we take any element from this group, let's say A from ZP star, and raise it to the power P minus 1, we will get the identity element. So A to the P minus 1 is equal to 1 modular pi. This is just by the third corollary. So, and that's it. This is how you prove the Little Fermat theorem using the Lagrange theorem. Okay, so these are 5 corollaries from the Lagrange theorem.
Could you repeat the third corollary?
The third corollary is this. So if we have a finite group and we have an element from this finite group, then if you raise this element to the order of the group, you will get the neutral element, the identity element. And here is how to prove this.
And so, can I ask you to return to the claim itself?
Which one?
The first one, not the corollary, but yeah, this one. Thank you.
Oh yeah, the claim says that if you have a finite group and you have its subgroup, then the order of the group is the product of the number of cosets, which is the index of the subgroup, times the order of the subgroup. And using this, you just prove all the corollaries. Just in case, are there any questions?
Yes, can you please explain once again the fourth corollary? I'm not sure that I got it.
The fourth one?
Yes.
Okay, let's go again. So what are we given? we have a group G of order P, and P is a prime number. So now the claim says that if you take any element G, which is not identity element, then it's a generator for the group G capital. So the G capital is cyclic automatically. So this is the claim. Now, how do we prove this? Just take an arbitrary element G, small, from G capital, which is not identity, and generate the cyclic subgroup. So you can always generate a cyclic subgroup by any element. So this is a subgroup inside G. We don't know if it's the whole group G or not. So it's just a subgroup. But since this is a subgroup, its order divides the order of the group itself. But the order of the group is a prime number P. So you have only two options. This number is either 1 or P. But since the cyclic subgroup generated by G contains two different elements, which are the neutral element and the element G small itself. So they are distinct elements. This is here. So the second option is impossible because this thing contains at least two elements. So it cannot consist of one element only. So this option is impossible. So we have the second option. But what does it say? It says that this subgroup has exactly the same amount of elements as the whole group. So they must be the same. Is it clear now?
Yes, thank you.
Okay. Are there any other questions? Okay, so now I want to switch to a new subject. So that was a part of the previous lecture that I didn't cover the previous time, but now I want to discuss homomorphisms. Well, okay, so let me give you a definition. So we are given two groups, G and H are groups. Then I want to define a homomorphism phi from G to H, a homomorphism. As usual, every definition consists of two parts. First of all, we define some data and then pose axioms on those data. So phi must be a map of sets. So phi is just a map of sets. So it just takes elements from the group G to elements of the group H. And we have one axiom. Phi must preserve the operation in the following sense. For any elements G1 and G2 from the group G, phi of G1 times G2 equals phi of G1 times phi of G2, where here is a product in G, and here is the product in H. So what does it say? So you want to map one group to another one such that, well, it doesn't matter in which order you let's say it in a different way. So it doesn't matter whether you multiply the elements first and then apply the map, or you may apply the map to each element and then multiply them inside the other group. So the result must be exactly the same. So if you have a map preserving a multiplication in such a way, it means that this map is a homomorphism. So now let me give you several examples.
Can I just one question? So a map is a bijection, right?
No, bijection is a special map, which is a one-to-one correspondence. Here, it's just any map. A map is a rule which takes an element from G to some elements of H. So let me draw a picture. So
a function or a relation.
Yeah, it's just a function. So you may take different elements to exactly the same element, and there could be an element here which is not an image of something from G. So
And
This-
is it true that every element of G has an image?
What
Like
again?
for map? I mean, for map, it's true that every element of G has an image.
Yeah. So for every element of G must go to some element of H. So the map must be defined on the whole set G.
Okay, thanks.
For example, if you take a map, if you take a rule, let's say, which takes x to the 1 over x, this is not a map. Because it's not defined at 0. You don't know where to take 0 element. So this is not a map.
And is it true for this phi that one element from G can't have two matches in H?
Yeah. The image is well defined. So
Yeah.
if you take an element from G, it goes to exactly one element in H. So you cannot have multiple images.
Yeah, thank you.
So it's like, well, yeah, it's exactly what the function is, a procedure, or there are a lot of different names. So usually we use the name map or mapping. There are, okay, are there any other questions?
So is it only for multiplication or it does work for other operations?
Well, but what are the other operations? If you are given a group G, then you have this specific operation on the set G, which is this one. And if you are given a group H, you have this specific operation on the group H, which is this one. So you must preserve these two operations in this sense, but you may have no other operations on these sets. I mean, well, saying that you are given a group, it means, well, when I say that we are given a group, it means that we are given a set and an operation. And the fact that phi is a homomorphism means that it preserves that particular operation that is given for this specific group. So if
it isn't necessarily true that operations in both H and G are similar, the same. So it may be different operations. Yeah.
But well, G and H are different sets. It doesn't make sense to say that operations on different sets are the same.
I see. Yeah. Thank you. Sorry.
No problem. Okay, let's give. Well, I want to give you an example, like several examples. I hope this will help you to understand the concept. Example number 1. Well, let's take G to be the set of permutations on n elements, and let's take H to be the set of plus minus 1. And here, for the first group, the operation is composition, and for the second group, the operation is just multiplication. Now we have a map from this set to this set, which is given by the sign. So if we take a permutation sigma, it goes to the sign of sigma. And this map preserves the multiplication in the following sense. If you take the sign of sigma times tau, this is exactly the same as sign of sigma times sign of tau, where here it's a composition of permutations. This is a product in Sn. And here is just a product of numbers. So this is an example of a homomorphism. So this is a rule which takes all elements from this group to elements of this group, and it preserves the operation in this sense. Now, let me give you another example. Let's take G to be GLN of R, which is the set of all non-degenerate matrices. So these are all matrices, square matrices, such that the determinant of A is not equal to 0. And the operation here is multiplication. And let's take H to be R star, which is the set of all real numbers without zero. And the operation here is also a multiplication of numbers. So here is a multiplication of matrices, and here the operation is a multiplication of numbers. And now we have a map from this set of matrices to non-zero numbers, which takes each matrix A to its determinant. So why is this map a homomorphism? Well, because if you take a determinant of A times B, where A and B are square matrices, then its determinant is the product of determinants. So this is exactly the rule for the homomorphism. And here you have multiplication of matrices, of matrices in GLN. And here we have a product of numbers, so in R star. So this is another example of a homomorphism. And as you can see, it's not a bijective here. And also the first example was an example where the map is not a bijection, because different permutations may have the same sign, and here also different matrices may give you exactly the same determinant. So this is a not one-to-one correspondence. But the map must be defined on the whole set. And let me give you another example with an additive notation. So example number 3, if you take Z plus as a group G, and well, let's say H to be also in the group Z with addition, then a map, let's say phi k, where k is just a fixed, some fixed integer. So let's define the map phi k, which takes an element m to the element k times m. So you just multiply by a fixed integer k. So multiplication by k. So this map is also a homomorphism. So why? Well, because if you take phi k of m plus n, this is exactly the same as km plus n, which is km plus kn, and this is by definition phi k of m plus phi k of n. And as you can see, well, here you use the operation from the left z, and here you use the operation from the right-hand side z. So this is another example of a homomorphism. Okay, now let's discuss several properties of homomorphisms. But just in case, are there any questions regarding the examples? Should I repeat something or clarify the details? Okay. Now, the claim. Well, suppose we're given a homomorphism of two groups. Phi, which goes from G to H, a homomorphism. Well, when I write something like this, I assume that G and H are groups. Otherwise, it doesn't make sense to say that phi is a homomorphism. So I do not specify this here. So I do not say that G and H are groups, but this is what I assume automatically here. But just in case. So then phi of 1 is equal to 1 always. So every homomorphism takes the identity element to the identity element. So here on the left-hand side, 1 is the identity element from G, and here on the right-hand side, 1 is the identity element from H. So this is what always happens. The property number 2 says that if you take phi of G to the minus 1, this is exactly the same as take phi of G and then to the minus 1. So for every element G small from G capital, we have this equality. So phi preserves, well, if you want to say it briefly, then if phi preserves an operation, then phi preserves the neutral element, and it takes the inverse to the inverse element. Okay, so now let's prove this. So claim number 1. Well, we know that 1 times 1 equals 1 in the group G. So this is the equality in the group G, just because of the definition of the identity. Now we might apply phi to the left and the right hand side of this equality. So since these expressions define exactly the same element, then their images must be exactly the same. So since 1 times 1 equals 1, then the image of the 1 times 1 is exactly the same as the image of 1. But now, since phi is a homomorphism, it preserves the multiplication. So here you have phi of 1 times phi of 1. And this is a sequence of equalities in the group H. So phi of 1 is an element from H, such that this equality holds. But now, since every element of H is invertible, you may multiply this by phi 1 to the power of minus 1. And this simply means that you can cancel this thing, and you will get phi of 1 equals 1. So this is why, if you have an identity element on the left, it goes to the identity element on the right. Are there any questions, just in case? Okay, so now, how to prove that phi preserves the inverse elements? Well, let's take an arbitrary element G from G capital, and we want to prove these equality. As you can see, we want to prove that something is equal to an inverse of phi of G. In order to prove this equality, we need to show that the left-hand side satisfies the definition of the inverse element. And since the inverse element is unique, this will prove the equality. So in order to prove that the blue element is the inverse for phi of G, we need to show that phi of G times phi of G inverse equals 1, and phi of G inverse times phi of G equals 1. So if we can prove these two equalities, then it will simply mean that this equality holds, because just by definition of the inverse element, and the fact that the inverse element must be unique. Okay, I want to check the first condition. The second one is done in a similar way. Well, let's consider this this expression. Because phi is a homomorphism, it preserves the multiplication, so you can rewrite this in this form. And now, since G and G inverse are inverse to each other, this is exactly the same as phi of 1. And because of the previous item of the claim, this is 1. And that's it. So this is how you prove this. So the later computation was in the group H, just in case. So all these elements are in H. So this is the claim and the proof. Are there any questions?
Yeah.
Okay.
Maybe that's something stupid, but why is it sufficient in the second part? Why is it sufficient to show that this system
Okay.
suffices?
So let's recall the definition of the inverse element. So if we have an element G from the group G, then an element, let's say H, is called inverse of G if it satisfies these two equalities. And we know that this element is unique.
Oh,
And
yeah,
because of that, okay?
Yeah, it seems clear, yeah.
Okay.
No, it's not clear. Can you continue?
Okay. So since it's unique, we may give him a unique name, which is G to the inverse. So now, if you take any other element let's say W, and you can prove that G times W equals 1 and W times G equals 1, then it means that W is also the inverse of G. But since the inverse is unique, W must coincide with the element H. So here, you see the right-hand side is the inverse of the element phi of G. And here we show that this element satisfies these two conditions for being the inverse element of phi of G, because we multiply phi of G on the right and on the left by this element. And
Okay, thank you.
Okay, cool.
So can I also ask a question about proof of identity element? I didn't exactly get how we did it.
Okay, let's repeat it one more time. So first of all, let's take the neutral element from the group G. It's 1. Then I just consider this equality. This is a so this is true, because if you multiply 1 by 1, you will get 1. This is just by definition of the neutral element. And now, so this is the place where you need to guess where to start. So this is just a trick. Just consider this expression, and this expression equals to the neutral element itself. Now you apply your homomorphism phi to the left-hand side and to the right-hand side of this expression. Since these expressions are equal, so they give you exactly the same element, their image must be exactly the same. So applying phi, you will get this equality. But now, so is it clear by now?
Yeah.
So now you use the fact that phi is a homomorphism. So phi of the product is the product of phi of phi's. And now let me write it here. You have this equality. Phi of 1 times phi of 1 equals phi of 1 in the group H. And now you multiply this equality by phi of 1 to the power of -1, let's say on the right. If you multiply this on the right, you will get this. Let me write it down here. Phi of 1 times phi of 1 times phi of 1 inverse equals phi of 1 times phi of 1 inverse. And now, by the definition, this product and this product is the identity element. So you will get phi of 1 times 1 equals 1. And because phi of 1 times 1 is phi of 1, you will get this equality. And this must complete the proof.
Okay, thank you.
No problem. Are there any other questions? Okay, cool. Let's go. Let's do this. Okay, now I want to discuss why do we need homomorphisms. Well, actually, homomorphisms is a way to compare two groups. But if you want to compare different groups, you want to have a way to say that two different groups are actually the same. And there is a notion of isomorphism for doing that. So suppose we have two groups, G and H, are groups. Then I want to define an isomorphism. I will denote it like this, an isomorphism. So an isomorphism is a map. So it's like a homomorphism, it's just a map. But it must preserve the operation, and it must be bijective. So it preserves the operation. And the second axiom says that phi is a bijection. So these two conditions simply say that phi is a homomorphism which is bijective. So this thing means that phi is a homomorphism. And it's a bijective homomorphism. So a remark, isomorphism is the same thing as bijective homomorphism. So let me explain the meaning of this definition. So if you have two groups, let's say G and H, well, what does it mean that these two groups are the same? Like you have a group and some operation here on the set G, and you have a set H and some operation here on the set H. So how do you compare them? First of all, you want to say that you have exactly the same amount of elements. In order to do that, you need to find a bijection. A bijection is a one-to-one correspondence, which means if you're given an element here, it corresponds to a unique element here. And if you're given some other element here, it corresponds to another element here. But a bijection is not enough, because the bijection knows nothing about these two operations on the sets. Now we want this bijection to be compatible with operation. What does it mean? It means that if you're given two elements here, let's say A and B, you may produce their product using the rule for the group G, and you will get some element A times B. And now this element is in one-to-one correspondence with some other element here in the group H. And the fact that phi is also a homomorphism means that if you multiply these two guys, which correspond to the initial elements, you will get the same element here. So this must be phi of A times B, and also it must be phi of A times phi of B. So roughly speaking, if you have an isomorphism between two groups, these two groups are exactly the same. So like their elements may have different names, but because of this bijection, preserving the operation, you have like a translation of the names from the group G to the names of the group H, and such that this translation takes the operation from G and it appear to the operation on H. So this is how you should think of the isomorphism. So, and the reason why we need isomorphism, well, if we want to understand the structure of a group, you can change this group to another group, which is isomorphic to initial group G. So if you have an isomorphism between G and H, and you change G to the group H, so the group H has exactly the same structure as the group G, because the isomorphism between them means that they are exactly the same. All the properties that you may formulate in terms of operation, they're exactly the same. So they have exactly the same amount of elements of specific order. They have exactly the same amount of subgroups, and so on and so on. So all the properties are exactly the same. And this bijection is just the way to transform one group to another one. So this is how you should think of it. Moreover, if you have a bijection, you always have an inverse map. So the inverse map is also a bijection, and it's also a homomorphism. So you always have a map in the opposite direction, which also preserves the operation. So it's clear from this picture that the inverse map preserves the operation, because the product of these two guys, if it corresponds to the product of these two guys, then in the opposite way, it goes exactly to this product. So this is how you should think of it. Let me give you several examples. I hope this will help to understand the concept. But just in case, who thinks that the picture was clear and it's clear what I wanted to say?
It is absolutely clear.
Yeah.
Okay, then it's fine. So now examples. Let's take G to be Zn with the addition at the operation. And let's take H to be mu n, which is the set of all complex numbers with the condition z to the n equals 1. And the operation here is multiplication. Well, I claim that these two groups are isomorphic. Well, let's take psi from mu n to be a primitive root of unity, a primitive of 1. Then we may consider a map which takes any remainder k to the kth power of psi. Well, first of all, because psi is a primitive root, this map is a bijection. Pardon. Something happened. Okay. So because psi is a primitive root, this map is a bijection. And now it's, well, you may check that if you take k plus m, so the operation here is a sum modular n. So if you take k plus m, well, let's say this is phi of k. Yeah. So, and you take phi of k plus m, this is exactly the same as psi to the power of k plus m. Oh, I'm sorry. Here you should, I'm sorry, k plus m modular n. This is the operation. And this is phi of k. So if you take this thing, it goes to psi to the power of k plus m modular n. But since psi is a primitive root of order n, then this is exactly the same as psi to the power of k plus m, because psi to the power of n is equal to 1, and then this is psi to the k plus psi to the k times psi to the m, and this is exactly the same as phi of k and phi of m. What was the mistake? Oh, okay. So as you can see, if you take, so here, if you take two elements and multiply them in Zn, then this is exact, and then apply phi, the result will be exactly the same as you apply phi to each element k and m, which is here, and then apply the operation in the group mu n. So this operation is in the group mu n, and this operation is in the group Zn. So this map phi is a homomorphism, and it's bijective. So this is an isomorphism. So there is no difference between the group of roots of order n and the group Zn. So their structure is exactly the same. So if you want to study this group, is exactly the same as to study this group, and vice versa. Here is another example. Let's take Z with addition and the group of square matrices of the form like this, and n is integer, and the operation is multiplication. So then the map from Z to this group, given by the formula k goes to 1, k 0, 1, is actually a bijection, and it preserves the operations. So it takes addition of integers to the multiplication of matrices. So I don't want to check this. I would like to leave this as an exercise. So this map is actually an isomorphism. And here is another example of isomorphisms. Let's say you have a cyclic group G, and G small is a generator. Then we have two options. The option number 1, the order of the element G is infinite. Then you may take a map from Z to G, which takes each element K to the kth power of the generator G. I claim that this map is an isomorphism in this case. I do not want to prove this here, but it's clear that this is a, well, actually it's obvious, because since one order of G is infinite, then all powers are distinct, then this map is a bijection. But then we know the rule how to multiply the powers. So if you multiply G to the K and G to the M, it's exactly the same as to add two integers and then raise to the sum, to the power of the sum of these integers. And if we have the order of G to be n, then we have exactly the same result, but with Zn on the left. So we have a map from Zn to the group G, which takes each remainder modular n to the G to the K. And one can show that in this case, when the order of the group of the element is n, this is also a bijection. But okay, the fact that this is a bijection we already know from the classification result, because all the elements here must be powers of G from 0 to n-1, and then a simple computation shows that this map preserves the operation. So this is also an isomorphism. So this is another example of an isomorphism. Okay. Are there any questions regarding these examples? Well, so now I want to discuss some properties of a homomorphism. So if we are given a homomorphism, sorry, wrong color. So if we're given a homomorphism from a group G to a group H, then a homomorphism. Then we may define two subgroups. Well, first of all, two subsets. The kernel of phi is the set of elements G small from G capital, such that phi of G small is equal to 1. So all the elements from G capital go into the neutral element in H. So this is a subgroup in, this is a subset in G, but this will be a subgroup. Well, we will prove that this is a subgroup. And the second thing is the image of phi, which is the set of all elements of the form phi of J inside H, for all J small in G capital. And this is a subset in H. So these are the definitions. And the main result about these two guys is this claim. So if phi is a homomorphism from G to H, then tangent number 1, the kernel of phi is a normal subgroup. The second, the image of phi is a subgroup. Then number 3, phi is surjective if and only if its image coincides with H. Well, this is probably one of the most stupid items here. And the last claim says that phi is injective if and only if the kernel of phi consists of the neutral element only. So these are all the facts that you need to know about kernel and the image. Okay, let's try to prove this. First of all, let's take the kernel of the homomorphism. Then, in order to check that this is a subgroup, we need to check 3 things. First of all, a neutral element must be inside the kernel. Second, if 2 elements are in kernel, then their product must be in kernel. And if an element is in kernel, then its inverse must be also in kernel. So if we check these three properties, then it means that the kernel is a group. Okay. Let's see. Well, the item number one we already know. Well, how to check that something is inside the kernel? Well, in order to check that, well, an element is inside the kernel if and only if, just by definition, if phi of A is equal to 1. So we can see that phi of 1 is equal to 1 because we already know this property, that the first one holds. Now, the second one, let's prove that A times B belongs to the kernel if A and B are in kernel. Well, this is because we may apply this property of the homomorphism, and since both these guys are equal to 1, then the result must be also 1. So that this set is also closed under multiplication. And because of this property, phi of A inverse is equal to phi of A inverse outside of the parenthesis, then we see if this guy is 1, then this is also 1. So if A is in kernel, then its inverse is also in kernel. So this means that the kernel is a subgroup. So we have checked all the properties. Now, we want to show that the kernel is a normal subgroup. What does it mean? Well, we have several properties we have a criterion how to check that a group is a normal subgroup. One of them says that for each element G from G capital, we need to show that G times the kernel of phi times G inverse must be inside the kernel of phi. So if we prove this, then it follows that the kernel is normal subgroup. Is normal by one of the properties from the previous lecture. Okay, let's take an element from the left-hand side. An element from the left-hand side has this form, where A is in the kernel of phi. And we want to prove that this guy is in the kernel of phi. How to check this? Let's take phi of this element and show that the result is 1. Because phi is a homomorphism, we have this. But since A was in the kernel, this element is 1. So we may cancel this element, and we will get this. And now you have several options how to continue the proof. For example, you may use the property of a homomorphism again. Then you will get this, and the result of phi of 1 is 1. So this is how so this equality, I mean this one, shows that the element GA G inverse belongs to the kernel of phi. So that's why this equality, this inclusion holds, and that's why the kernel is a normal subgroup. Well, the second part can be proved in exactly the same way as the first one. So I want to skip the proof of the second claim because this is done in a similar way. The third one is just by definition. Well, let me recall that the third claim says that phi, image of phi equals H if and only if phi is surjective. But, well, this is just the definition of the surjectivity. And the later claim says that phi is injective if and only if the kernel of phi contains only one element, which is the neutral element. Let's prove that. Let's go from the left to right. Well, so we know that phi is injective, and we want to prove that every element of the kernel is the identity element. Let's take an arbitrary element here. this means that under our homomorphism phi, the element G goes to the neutral element. But we also know that the neutral element of the group G always goes to the element 1. So we have two elements, G and 1, and they go to exactly the same element 1 on the right. Because of the injectivity, this means that these two elements are the same because phi is injective. So this proves that every element of the kernel must be the neutral element. So it contains only the neutral element, and that's it. In the opposite direction, we know that the kernel contains only the neutral element, and we want to prove the injectivity. So let's take two elements, G1 and G2, and assume that they go to exactly the same element. Then we may multiply this on the right by phi G2 to the -1. And we will get this equality. Now, using the fact that phi is a homomorphism, we can rewrite this as this, and then also like this. But the later equality, just by definition, means that G1, G2 inverse belongs to the kernel of phi. But by our assumption, the kernel of phi consists of one element, which means that G1, G2 inverse is equal to 1. And multiplying these by G2 on the right, we will get G1 equals G2. So we have shown that if we are given two elements, G1 and G2, and phi, the image of G1 and G2, the images of G1 and G2 are the same, then the initial elements were exactly the same. So that was the injectivity. And this completes the proof. Okay, so are there any questions regarding the claim? Cool. Now I want to discuss direct products. So there are several ways to produce new groups when you're given some other groups. And one of the ways is to take a product of different groups. So if we are given two groups, G and H are groups, then consider their direct product, which is the set of pairs where G small is from G capital and H small is from H capital. So just all possible pairs of elements where the first element is from G and the second element is from H. So this is a direct product. Now, I forgot. Well, okay. So the direct product is the name of the group we're trying to produce. So now, so when I want to produce a group, I need to present a set, and then I must provide an operation of this set. So this is the set for the direct product. Now I want to produce an operation. So I want to take two elements from this set, which is G1, H1 is the first element, and the second element is G2, H2. And I want to explain how to multiply these two elements. And this is simply, and you do this simply coordinate-wise. So you multiply G1 and G2 and put the result in the first coordinate, and you multiply H1 and H2 and put the result in the second coordinate. So this is how you define the operation. So this is the definition for the operation. So now the set G times H becomes a group. So you may check that this is a group. In order to do that, you need to check the associativity law, but this is more or less straightforward computation, because in each coordinate the operation is associative. This operation must also be associative. Now, the identity element is a pair of the identity elements. So here the identity element of G, and here is the identity element of H. So when you apply this operation, it's clear that multiplication on the right and on the left doesn't change anything when you multiply by this element. And if you want to take an inverse element of the pair GH, this is exactly the same as taking inverse for each coordinate. So this is, again, a straightforward computation. You just multiply this guy by the pair GH using this rule, and you see that it satisfies the definition of the inverse element. So this is the way to produce a new group using some other groups. And also, if you have several groups like G1 and so on, Gn, you may produce a product of several groups. So the definition is exactly the same. So you take like all sequences of elements where elements on eth place belong to the eth group, and you multiply them coordinate-wise. Okay. Now, I want to discuss one of the most interesting objects in theory of groups. This is finite abelian groups. Okay. What is a finite abelian group? Well, as the name suggests, a G is a finite, let's say it like that, a finite abelian group if it's a abelian group and the order of G is finite. So G must be commutative. And the second, its order must be finite. So this is the finite abelian group. Well, it happens that we know the structure of all possible finite abelian groups. Well, here is the claim without proof. It's not an easy to prove, so I don't want to waste our time doing that. So if G is a finite abelian group, then G is isomorphic to a product of cyclic groups. So there are no other finite abelian groups. So every finite abelian group can be presented in this form. This form is not unique. We will discuss the uniqueness later. But somehow, if you have a commutative group with finitely many elements, you can always provide an isomorphism to a product of cyclic groups. For example, well, let me take an example. Let me give you an example. Well, if we have like Z8 star with multiplication, well, this is a finite abelian group because it has finitely many elements, and so it must be isomorphic to a direct product of cyclic subgroups. So I don't want to prove how the isomorphism, well, I want to show the isomorphism, but I don't want to prove why the map is an isomorphism. So let's discuss, let's count all the elements of Z8. So all the elements of Z8 are the numbers from 0 to 7. Now, if you want to take Z8 star, it means that you need to take all elements of Z8 that are co-prime with 2. So you just exclude this set. So Z8 star consists of 1, 3, 5, and 7. And the operation here is multiplication. Well, it turns out that Z8 star is isomorphic to Z2 times Z2, and the isomorphism works as the following. The element 1 corresponds to 0, 0. The element 3 corresponds to 1, 0. The element 5 corresponds to 0, 1, and the element 7 corresponds to 1, 1. Well, one may check that this, well, it's clear that this map is a bijection because we have a one-to-one correspondence, but one can check that this map is actually a homomorphism. So, this shows you that well, some group that we already know can be presented in a specific form, which is a product of cyclic subgroups, of cyclic groups. Okay, now, well, I believe we will check this property during the seminar session, but now I want to switch to different claim, which is the Chinese remainder theorem. Well, the Chinese remainder theorem explains how to transform one abelian group, finite abelian group, to another finite abelian group. Chinese remainder theorem. Okay, so suppose we are given two co-prime non-zero natural numbers. Then, when we produce a cyclic group ZMN and a product of two cyclic groups ZM times ZN. So the Chinese remainder theorem says that if M and N are co-prime, then we have a map. Well, we have an isomorphism between these two groups. And the isomorphism work as the following. You take an arbitrary remainder here, and you take it to K modular M, comma K modular N. So this map gives you an isomorphism between the left and the right-hand side. So this is the Chinese remainder theorem. So are there any questions regarding the claim of the theorem? Okay, let me show you how to prove the result.
Wait, could you just repeat it again?
Okay, so we have two groups, ZMN, which is a cyclic group of remainders modular Mn, and a product of Zm and Zn, a direct product, which is just a set of pairs where the first element is a remainder modular n and the second element is a remainder modular n. So elements here are just pairs. And now I claim that if M and N are co-prime, so their GCD is 1, then this map given by this rule is an isomorphism between these two groups. Just in case, the operation here, here, and here is an addition, well, modular corresponding number. So, yeah.
What is, well, ZMN, MN in the index of ZMN?
Oh, okay. Let me be more precise and give you an example of what's going on here. Let's take M to be 3 and N to be 2. Then M times N is 6. So the claim says that Z6 is isomorphic to Z3 times Z2. So Mn is just a new number, which is a product of M and N.
Yeah, it's clear now. Thank you.
Okay. And yeah, and this map actually given by the formula K goes to K times K comma K. You just reduce the remainder modular the corresponding number and you will get the map. Are there any other questions regarding the claim? Okay, so let's prove this. We have like 10 minutes, if I'm correct. Just in case, am I right that we have 10 minutes?
Yes.
Yes.
Yeah.
Oh, cool. That's good because I don't want to fail this time. I want to end when I'm supposed to end the lecture. Okay. First of all, we want to we have this map. Well, by the rule, K goes to K modular M, k modular n. So we have a well-defined map. So this is just a map of sets, because you can take each element from the left-hand side and take it to an element, a specific element on the right-hand side. So this is a well-defined map. So what do we want to check? We want to check two things. The thing number one, we want to show that phi is a homomorphism. So it preserves the operation. And the second thing we want to check, that phi is a bijection. So this is what we want to prove. We want to show this. Okay. First, I want to check that phi is a homomorphism, that the map preserved the operation. But this is a straightforward computation. Let's take k and let k1 and k2 from ZMN. Then put k1 plus k2 modular mn and apply phi. Well, just by definition, this is what? You should take k1 plus k2 modular mn to an element modular n, which is k1 plus k2 modular n, modular m, comma k1 plus k2 modular n. So this is what you should do by this rule. Just take this element and reduce it modular m, and then reduce it modular n. So here it must be m. It's written hopefully. So this is just by definition of this map. But now, by definition of the operation on the direct product, what's written here is actually a product of k1 modular m and k1 modular n. Let's say a sum. Well, I have a choice how to denote the operation in the product. So I want to denote the operation by the sum, by the sign plus. So what's written here is just this. Because you need to add these two guys together, and you need to add these two guys together. This is exactly what's written here. But then, by definition of phi, this thing is just phi of k1, and this thing is just phi of k2. So as you can see, we have this equality. So this thing is equal to the product of these guys, and this is exactly, well, not product, but plus. And this exactly means that phi is a homomorphism. So phi preserves the operation. Okay, now I want to show that phi is a bijection. Well, if I want to show that phi is a bijection, I want to show that phi is an injection. Phi is injective. And then I want to show that phi is surjective. So first of all, I want to prove that the injectivity of phi. Well, let's do this. But in order to check the injectivity, we know that phi is injective if and only if the kernel of phi consists of the neutral element only. So let's take an arbitrary element from the kernel and check that this element is 0. So let's take an arbitrary k from ZMN and compute and solve this equation. So phi of k, just by definition, is k modular m, comma k modular n. And we want it to be 0. But what does it mean that this equality holds? This means that m divides k and n divides k. And now we use the property that m and n are coprime. Because of this, the later two conditions mean that m times n divide k. But now you can see k is a remainder modular m times n, and it's divisible by m times n. So there is only one option here. K must be 0. All other remainders are not divisible by m times n. So as you can see, if k belongs to the kernel, which is this equality, then k must be 0. So we have checked that the kernel consists of the neutral element only, so the map is injective. Now let's check that the map is surjective. And here I want to use a trick. You see, we have a map from ZMN to ZM times Zn, which is injective. Now, if we want to show that the map is surjective, it's sufficient to show that this map contains the same amount of elements, or this set contains the same amount of elements as this set. So how many remainders in this set? Well, there are exactly m times n elements. But how many elements in the direct product? Well, since the direct product is the set of all pairs, then there are these many elements. But this is, again, m times n. So we have an injective map between two sets of the same cardinality. So because of this map is automatically surjective. That's it. Okay. And now I have like 2 minutes, and I want to formulate another claim, which is really important for us. But before doing that, because of the Chinese remainder theorem, you see we have this. Z6 is isomorphic to Z2 times Z3. So these two groups are actually the same. So exactly the same group has different presentation in the form of product of cyclic groups. So here we have like one factor, one cyclic factor, and here we have two cyclic factors. But it looks like these groups are different, but they are actually the same. And the Chinese remainder theorem provides an isomorphism between these two groups. But if we take something like Z4 and Z2 times Z2, these two groups are not isomorphic. Well, one can show this. And the reason is, well, every element on the right-hand side has order 1 or 2. And on the left-hand side, there exists an element of order 4. But if the group were isomorphic, they would have exactly the same amount of elements of order 4. But since the amount of elements of order 4 is different, they are not isomorphic. So how to check, well, if the two groups are isomorphic or not? And in order to do that, we have another claim which explains how to compare two finite abelian groups. Let me formulate this claim. So if G is a finite abelian group, then there are two unique representations of the group G. Then there exists a unique representation of the group G in the form like this, where the integer d1, d2, and so on, they divide each other and they're strictly larger than 1. So each finite abelian group can be uniquely presented in this form. And also, there is a different claim which says that every finite abelian group can be presented in the other form uniquely. Let me write down the form, and then I will explain what it means. Here, P1 and Pm are prime numbers. pi r prime with repetitions. And up to permutation of factors, this form is also uniquely determined. So yeah, and numbers k1, so km are greater than 1. So they are not 0, so 1 and larger. So every abelian group can be presented in one of these two forms, and these forms are unique. So if you want to compare two different abelian groups, finite abelian groups, you must first find and represent them in one of these forms. And when you represent them in one of these forms, you just simply compare these forms, and if they are the same, so the groups are isomorphic, and if they are not the same, the groups are not isomorphic. So I want to provide a final example for this result, and this will be the end of the lecture. I see that I have like -2 minutes, but I hope that's not crucial. So let's take Z2 times Z6 and Z12. Well, this is exact. So this is the group. This is a group G, and this is a group H. Then the group G has like 12 elements, and the group H also has 12 elements. And as you can see, this is the first form from the claim. So here you have two cyclic factors and 2 divide 6. And here you have only one cyclic factor, and there are no condition for the division. So since these presentations are different, these groups are not isomorphic. Or you may reduce this presentation to the form number 2 using the Chinese remainder theorem. We already know that Z6 is isomorphic to Z2 times Z3. So the whole group is isomorphic to Z2 times Z2 times Z3. So this is a presentation for the group G as a product of cyclic groups, and the order of each cyclic group is a power of prime. Here, 2 to the 1, 2 to the 1, 3 to the 1. And here, using the Chinese remainder theorem, you represent 12 as a product of 4 and 3. 4 and 3 are coprime, so Z12 must be isomorphic to Z4 times Z3. So this is also your H. But as you can see here also, Z4 and Z3 are cyclic, and the order of each cyclic subgroup of each cyclic group is a power of a prime number, 2 to the 2 and 3 to the 1. And this is the second form from the previous claim, which is this. And as you can see, they are also different. So here you have one factor Z3, but the other part is different. Since in this form the presentation is different, these groups are not isomorphic. So it's sufficient to check one of these two representations, but I just wanted to demonstrate both conditions from the previous claim in this example. So this is how to compare different finite abelian groups. Okay. So are there any questions regarding the lecture?
Yes, there are. Okay.
The question is about annotation. Like in some places we denote 1 as a neutral element, however groups are like arbitrary, and we could take, for example, the 8 where a neutral element is 0. So is it correct to like write 1 as a neutral element for every group?
Could you repeat the question, because there was a problem with the sound?
We denoted in some places 1 as a neutral element.
Oh, okay. So you see, when I write 1, what do I? Okay, when you're given a group, let's say, it may be a set G with an operation denoted by point. You may have a set W with an operation denoted by something like this, or you may have a set T where like you may denote the operation by heart or whatever. Well, if these sets are groups, they have a special neutral element, and this neutral element must have some name. Well, usually you denote it by the element 1, but you may denote it by any other symbol. You may use this symbol to denote the neutral element, or I don't know, you may use something like this. It doesn't matter, but you just need to point to a neutral element, and this neutral element must have a name. So when you take, let's say, Z8 star and multiplication, then the neutral element is 1, where 1 is the name of the natural number. This is, so here 1 is just a symbol. It's not a name of the natural number, because if your group G is something like permutation, there is no element 1. There is no natural number 1 inside permutations, but you have the identity element. But for simplicity, you just denote the identity element by 1. Well, but when you deal with Z8 star, you have 1 as the natural number, and by coincidence, it coincides with the neutral element of the group. But if you take Z plus, here the neutral element is 0 and not 1. But what is important is to understand which element is the neutral element. And in order to be, well, in order to make this process simple, people use two different notations. When they use multiplicative notation, they denote the neutral element by 1, and when they use an additive notation, they denote the neutral element by 0. So this notation just coincides with the natural notation in these cases. For example, in the case of Z plus, the neutral element is also denoted by the symbol. Well, the neutral element is 0 natural number, and it's denoted by the 0 symbol using this notation. But I mean, this is just a notation. When people prove something for a group G with multiplication, it simply means that when you use your group, you replace G by the corresponding set, you replace your operation by the corresponding operation on the group, and you replace your neutral element by that specific neutral element that must be instead this abstract neutral element, which is denoted by 1. So this is just a name. It doesn't mean that the natural number 1 belongs to your group and the natural number 1 is the neutral element. No, this is just a name, and it's very convenient to denote the neutral element by 1. Well, I don't know. Well, I was trying to explain something and clarify what's going on with notation, but did it make your life easier?
Why didn't we just use, for example, letter E that we used previously?
Oh, because well, there is no good answer to this question. I believe the letter E would be much better in order to avoid confusion. But since I used to use 1 as the neutral element for a group with multiplicative notation, well, I automatically write 1 instead of E each time when I see multiplicative notation for the group. This is just a habit. And this is the habit that mathematical literature has. So if you see any paper or like textbook on algebra, you'll see that people use 1 to denote the neutral element, and they rarely use any other symbols.
Okay.
Are there any other questions?
Yeah, can I ask a little question? Can you show the proof for the injection in Chinese remainder theorem again?
Yeah, give me 1 second. Or it should be here. Yep. So should I go through the proof?
Yes, only for the injection.
Yeah. So you see, so how do you prove injectivity? Because of this property, phi is injective if and only if the kernel contains the neutral element only. The neutral element in this group is 0. So we want to prove that the kernel of this map contains only 0 element. Okay?
Yeah, it's clear.
Now, let's find all the elements K from this group that goes to the neutral element in the product. So we want to find all K satisfying this equality, because this guy is the neutral element for the product.
Yes.
So now, by the definition, phi of K is what? Is A modular M comma k modular n.
Yeah.
But and we want this to be 0, comma 0. So
Yes.
k modular m must be 0 and k modular n must be 0. When this happens if and only if m divides k, then the first thing must be 0. And if and only if n divides k, the second part is 0. So we have these two conditions.
Yes. Yes.
So, but now when m and n are coprime, this is equivalent to this condition.
Yeah, that's clear for now.
Okay, cool.
And another question.
Yep.
In the example with that 4, which isn't isomorphic to the Cartesian product of Z2 and Z2, so by the claim that is going later than that, Z4 must have a representation, such a representation.
No, by this claim, this is the second representation. Well, this is the second and the first. Well, I mean, the second and the first representation for the left and the right hand side is the same. I mean, let's say this is the second representation. So this is z of order 2 to the 2. So just one factor of this form. And here you have two factors of this form.
Oh, yeah. Yes.
And you see these two are different. I mean, they are of this form, but they are different. So they must not be isomorphic.
Yes. Okay.
So they are not allowed to be isomorphic.
And another real question. That was before the Chinese remainder theorem claim. There was an example with Z8 with a star.
Okay, let me. Oh,
right before the Chinese.
I'm sorry. There, yeah, that's
yeah. Here. So why do we use exactly such a bijection? Well, we map 1 to 0, 0, 3 to 1, 0. Why don't we, for example, map 3 to 0?
There are other. Well, actually, this is not this is not the only option. There are three different options.
Yeah,
here.
It's clear. That's just.
But I just wanted to say that there is at least one isomorphism, and here is an example of an isomorphism. But yeah, you're right. There are other two examples of isomorphism.
Yeah,
it's not unique.
Seems clear. Thank you.
Okay. Are there any other questions?
I have a question about when we write Z8 star without, I mean, with this dot, we mean that it's a group, right? So it should only have elements 1, 3, 5, 7, right?
Yep.
And it's like the definition of Z n star.
Yeah, you take all remainders coprime with n.
Zn. And we had this definition like today for the first. I mean, they are coprime, because I mean during last seminars and lectures we didn't really discuss this thing. I mean, we didn't discuss that it's only coprime once. So
I mean, I see.
The question is if for example in homework where the task was for Z8 find all subgroups, I found all subgroups which are like correct for this 0 for this 1, 3, 5, 7, but I wrote that Z8 itself is not a subgroup of itself because it's not a group, because it has 2, 4, and 6. It's a mistake, or it's like
I'm not sure that I understand your question. So I mean, if you are given Z8 star with a product as a group and you want to describe its subgroups, then Z8, well, it's a larger set containing this group. But when you describe subgroups, subgroups are subsets. So Z8 is not a subset of this thing. So it doesn't make sense to say that Z8 is a subgroup of Z8 star.
I mean, for example, if I named the subgroups correctly, but I also wrote for some strange reason that this Z8 is not group because because it has 2, 4, and 6. It's a big mistake, and I should kind of fix it, or it's all right. I mean, I just still have time to kind of remake something, and that's the question.
I'm not sure that I understand the question. Well, Z8 with multiplication is, of course, well, the 8 with multiplication is not a group.
Yeah,
That's true.
So it's all right to write that the 8 with multiplication is not a group.
But this problem has nothing to do with the exercise.
Yeah, I understand. It's just I just wrote that it's not a group, and I wonder if it's true or not. I mean,
but with respect to what operation? It's a group with respect to addition modular 8, but it's not a group with respect to multiplication modular 8.
With respect to multiplication.
Yeah, that's a true claim.
Okay, thank you very much.
No problem. Are there any other questions? Yep.
А можно вопрос задать? Вот у нас в самом начале теорема Лагранжа была, и вы написали формулу. Вот не совсем понятно обозначение в ней, которое следовательно и...
Вот это?
Да. Количество кассетов ваше.
Смотри, но обозначения не вводились на прошлой лекции. Вот здесь используют... just in case, there was a question in Russian, but is there anyone who wants to hear the question and the answer in English? I'm asking just in case. Окей. Значит, смотри, вот это так называемый индекс подгруппы, это количество смежных классов. То есть есть левые смежные классы, правые смежные классы, их количество одинаковое и обозначается вот таким числом. Вот это количество элементов в подгруппе, это количество элементов в группе. То есть как бы тоже здесь написано, что количество элементов в подгруппе умножить на количество смежных классов равняется количеству элементов в группе.
Осознал. Все. Спасибо.
Можно еще вопрос? Вот когда нас просят, допустим, найти количество коссетов, да, как еще на русском? Я не очень...
Смежные классы.
Да, смежных классов. Имеется в виду, вот, допустим, если у нас правые и левые совпадают, потому что она коммутативная, то мы типа пишем, что, допустим, их столько-то, но если считать их по отдельности, это число умножено на 2, или... Ну, то есть, у нас, как бы, если левые и правые кассеты совпадают, сколько у нас кассетов?
Нет, они считаются по отдельности, ну.
Ну, то есть, допустим, если у нас 2 левых кассета и 2 правых, они одинаковые, но у нас все равно 4 кассета.
Нет, у нас 2 кассета, потому что они просто, ну, смотри, то есть ты возьми множество, вот перестановки, возьми перестановки. Там есть четные и нечетные перестановки. Четные перестановки, значит, это как бы и левый, и правый кассет подгруппы четных перестановок, а нечетные – это и левый, и правый кассет тоже подгруппы четных перестановок. То есть потому что у тебя, ну, как бы то, что так оказалось, что как кассеты левые с правыми совпали, оно не удваивает тебе как бы количество кассетов.
То есть это как
только
бы...
для левых считаешь или только для правых считаешь?
Если у нас коммутативная операция, то считаем только одну сторону, как бы.
И даже когда не коммутативные, ты считаешь только односторонние. То есть вот эта штука говорит, что это количество только левых кассетов. Но и это количество, оно совпадает с количеством только правых кассетов. То есть это не левых плюс правых кассетов, это только левых кассетов или только правых кассетов. Просто это число не зависит от левых или правых.
Я понял, я имею в виду просто, что, допустим, вот у нас просто вот не связано с этой теоремой, просто, допустим, у нас есть столько-то левых кассетов и столько-то правых, и они совпадают, то мы, получается, просто вот задача найти количество кассетов. Мы какой ответ дадим? Что левые равны правым, поэтому их столько, или...
Ну, если у тебя например, если у тебя 3 левых кассета и 3 правых кассета, то у тебя, так и говоришь в ответе, левых кассетов 3, правых кассетов 3.
А если не совпадают, то все равно так и говоришь?
А какая разница? Тот факт, смотри, вот, скажем, если, не знаю, значит, ты, сейчас скажу, как этот... Вот есть футболка, да, вот как бы футболки, да, вот ты взял из кучи футболку, поносил, положил обратно, кто-то другой взял из кучи футболку, поносил обратно. Каждый из вас поносил по одной футболке. А была это одна и та же футболка или нет, как бы никого не интересует. Но вот здесь та же самая ситуация. Вот как бы тот вопрос, что кассеты совпали, это как бы ортогональный вопрос. То есть как бы...
Окей, спасибо.
Ну, то есть в сухом остатке ты просто говоришь так, что, ну, как бы у тебя вопрос такой, что тебя просят найди сколько левых кассетов для данной группы. Вот ты берешь, перечисляешь все левые кассеты, считаешь их, говоришь, сколько их. То, что левые кассеты совпали с правыми, тут никого не интересует. Это абсолютно не важно для этого вопроса. Ну, совпали? Окей. Не совпали? Тоже окей.
Спасибо.
Еще вопросы?
У меня есть вопрос.
Давай.
Почему Z2 на Z2 не равно не изоморфично Z4?
Но не изоморфно.
Да, не изоморфно.
Не проблема. Это, как сказать, я по-русски же не произносил, как это звучит. Значит, смотри. Есть два способа это объяснить. Есть способ с помощью теоремы вот этой последней. То есть из последней теоремы это просто вот автоматически следует.
Так они же делят друг друга. 2 делит 2.
Ради бога. Я хочу сказать, что еще раз. Вот это представление, скажем, вот такого вида, правильно?
Угу.
И вот это тоже представление такого вида. То есть
Да.
вот это группа G, а вот это группа H. Группа G представлена в таком виде, и группа H представлена в таком виде. Если они представлены в таком виде, то они изоморфны тогда и только тогда, когда этот вид совпадает. Вот это и вот это. Ну вот я смотрю на картинку, это совсем не одно и то же.
Не понял.
Ну, сравни вот эти две картинки. Одно и то же нарисовано.
Нет, ну в плане...
Нет, не одно и то же. Ну, например, вот тут нет крестика, а тут есть крестик.
Нет, ну Z6 же изоморфно Z2 на Z3.
Да, но Z6, когда ты говоришь Z6 изоморфно Z2 на Z3, то смотри, Z6 представлено в таком виде, но Z2 на Z3 в таком виде не представлено. Z2 на Z3 представлено в таком виде, а Z6 в таком виде. Ты не можешь их просто сравнить. Чтобы их сравнить, ты их должен представить в одном и том же виде. Если ты Z6 будешь представлять вот во втором виде, ты как раз и получишь Z2 на Z3, и значит получил то, что надо.
Сейчас вообще еще хуже стало, если честно.
Так, я чувствую, это надо на семинаре просто будет мне разобрать.
Я просто не понимаю, вот наше утверждение, да, наш клейм говорит, что найдется уникальный способ так представить и найдется уникальный способ так представить.
Да.
Вот. И что?
Ну смотри, это вот что означает. Если ты взял какие-то две группы, и обе представил в таком виде, то тогда они изоморфны, тогда и только тогда, когда такой вид совпадает. Вот Z6 и Z2 Декартова на Z3, они не представлены обе в таком виде. Z6 представлено в таком виде, а Z2 на Z3 в таком не представлено.
Почему?
2 не делит 3, 3 не делит 2. Хорошо, посмотрим, а представлены ли они обе в таком виде? Ну, Z2 на Z3 представлено. Здесь действительно 2 в какой-то степени, 3 в какой-то степени, а Z6 нет, потому что 6 это не степень простого. То есть они просто ни в таком и ни в таком виде не представлены обе. Одна представлена в таком виде, другая в таком. Поэтому тебе для одной из них надо пересчитать вид из одного вида в другой. И этот пересчет делается с помощью китайской теоремы об остатках. То есть ты Z6 пересчитываешь по китайской теореме об остатках, и она превращается в такой вид ровно Z2 на Z3. И видишь, что получилось Z2 на Z3. Это если ты применяешь вот эту теорему. Вот сейчас получилось понять, как эту теорему применить вот здесь? Ну или в Z2 на Z, или в случае Z6.
Мы хотим показать, что мы найдем один способ представить первым способом и найдем второй способ представить вторым способом. И потом хотим...
Нет, если ты хочешь сравнить, тебе надо выбрать способ первый или второй и представить каким-нибудь из них.
Хорошо, но 6 же мы не смогли представить.
Но ты с помощью китайской теоремы об остатках ты можешь переписать Z6 как Z2 на Z3. И вот ты представил Z6 во второй форме.
Но с таким же успехом могу... не могу.
Нет, не можешь, потому что 2 и 2 не взаимно просты, к сожалению.
Да,
или к счастью.
Так, ну хорошо, а почему Z4 не изоморфно Z2, Z2?
Но, опять же, если из этой теоремы, то просто у них они оба представлены, например, во втором виде. Ну вот, степень простого, степень простого, степень простого. И этот вид разный. Тут два множителя Z2, Z2, а тут один множитель Z4.
Мы доказывали эту теорему?
Нет, я ее не доказывал. Но если доказывать, то вот как можно сказать. Если две группы изоморфны, то у них одинаковые все характеристики, которые можно выразить с помощью операции. Например, какую вещь можно сказать? Давайте посчитаем количество элементов порядка 4 в левой и в правой группе. Если группы изоморфны, то это количество должно быть одинаковым, потому что, ну, как бы изоморфные группы, они одинаковые, если как бы, ну, одна и та же группа, это число должно быть одним и тем же. Но в правой группе все элементы порядка 2 или 1. Потому что любой элемент с собой сложи, ты получишь 0,0.
Мгм.
А в левой группе у тебя есть элементы 1 и 3. У них порядок 4. То есть в левой группе есть элементы порядка 4, справа нет элементов порядка 4. Поэтому эти группы не изоморфны.
Мгм. А такой вопрос. А P может повторяться, а D может повторяться? Вот
Значит,
в нашем теореме.
да, значит, с повторениями. D-шки могут повторяться, P-шки тоже могут повторяться.
Понял.
Вот, и здесь единственность с точностью до перестановки. То есть, если ты как бы переставил местами множители, ну, как бы считается, что это то же самое представление. То есть, надо как-то упорядочить простые и там их по степеням, например. Еще вопросы?
Понял, спасибо.
Окей. Ну, я смотрю, что через 3 минуты нам надо уже начинать семинар. Да, Маш, приходи тогда после семинара.
Да, хорошо.
А у нас семинар здесь же или...
Нет, по другой ссылке.
Хорошо.
Все, ладно, ребят, давайте тогда встретимся на семинаре.